All right, guys, just to get your juices flowing with identities again. So here's how you prove some identities. I picked some that were similar to the ones I put on that worksheet. Okay, so one of the things for the final is you need to try to remember the identities that you'll need as tools. For instance, what's the main Pythagorean identity? Can somebody remind me? Because I think we'll be using that on these ones.
Sine squared, cosine squared.
So sine squared plus cosine squared equals 1. Got to definitely know that one and its various variations. So we'll see if we need more than that one in a second. If we do, I'll show you how to pull it out. If you remember that one, you shouldn't need to remember the other two unless you want to do it that way. There's also some other identities like the negative angle identities. There's the reciprocal identities, which you guys should just know, like cosecant is 1 over sine, tangent is sine over cosine. Those ones I don't think you're going to have to work hard for. But you can remember from the graph, if you put negative into cosine, what happens? If you flip it this way, the cosine copies onto itself, so it becomes positive cosine. You should know that one. You should know if you put a negative into a sine, you have to flip it twice to copy it onto itself. So we went over all these once, and tangent works the same way as sine. So these are some of the types of identities that you should know. Okay, we'll see if we need any of those, I don't know. All right, so first problem. What do you guys think? Should we start on the left or the right?
Right.
Definitely the right.
Definitely the right. No. If you start with just one, there's like nothing you can do, unless you get really creative. So start on the left, write it down again. Uh-oh. All right, so then I would say, what do I want to do? So I think there's some stuff we can change secant and tangent into. Oh, so they're saying they want to distribute. They're expanding this. That's your choice. At this point, I see two options. Option number 1, distribute it. Expand it out. Multiply stuff. Option number 2, turn this into 1 over cosine. Turn this into sine over cosine. Same thing with those. And try to do a common denominator. I don't know which one's better. It's up to you. Multiple things might work. One thing might not end up working, and you have to try again. So this is about being flexible. So you guys are saying difference of squares is what it turns into? Because this is factored as difference of squares right now. So if you expand it and go secant times secant, you get secant squared. Secant times tangent, that's negative secant tangent. I'm not going to write it. Tangent times secant positive is the same thing. Those cancel out. And then tangent times tangent is tangent squared. Positive times negative. So it's kind of like difference of squares factoring in reverse. That's what these guys are telling you. Okay, you could just expand that even if you didn't see the difference of squares. Okay, so is secant squared minus tangent squared 1?
Yes.
If you know your identities, then yes. Where does that come from, though? It's not established. You can't be like, yes.
Or sine over cosine.
So if we just say yes on one.
Yeah, not enough. So I think going back to this identity, let's remind ourselves of this one. There's another version of this one. There's 2 other versions of this one. There's a secant squared version and there's a cosecant squared version. If I want the secant squared version to see if I can mess with that, I'm going to want to divide by cosine squared.
Tangent squared x.
Oh, I should use x, yeah. Oops. Okay, so that is tangent squared. That's 1. That's secant squared. Notice, do I have that memorized? This. No, the only thing I have memorized is this, which if you know anything about trig should be obvious to you because it comes from the unit circle. That's the most fundamental derivation from the unit circle, is that if you draw an angle in the unit circle, its sine is the vertical, its cosine is the horizontal, and its hypotenuse is 1. Do Pythagoras, that's what you get. Okay, so can I use that on this problem? Totally. Because that says secant squared is also tangent squared plus 1. So for this secant squared, I can put in tangent squared plus 1. I really shouldn't even have this other side over there at all. So this was this because we expanded it. From the Pythagorean identity, secant squared is tangent squared plus 1. If you drop the parentheses, because there's nothing to distribute, like terms, what's tangent squared minus tangent squared? Nothing. So you get 1. Oh yeah, that's what we were supposed to get. Sweet. Proven. Okay. Let's try this one. Which side do you guys want to start on?
Let's start on both at the same
You can't do that.
time. Like just
I don't think there's an obvious side to pick, so we'll just pick one, okay? Let's start with the left side. I don't know. Okay, what can we do with that?
You could change it to secant squared x.
We could probably use that identity over there. I think we're going to want to. The same one we just used, probably want to use that again. Before we do that, I want to do something else, though.
Change it to secant squared x.
This one had difference of squares factoring in it. This one has another kind of factoring if you want to do it.
Take them out.
What do they share?
Squares.
So I'm going to do that. Probably not the only way to do this, but I'm going to go with that. What's left if you pull secant squared out of secant to the fourth?
Secant squared.
Another one. If you pull secant squared out of itself, what's left, Jensen?
Secant.
If you pull secant squared out of secant squared, what is left?
X.
One.
Right. Let's try.
Why does the X cancel on the first secant point?
Why doesn't the x go away like what Jensen was saying, kind of?
Yeah.
Because this is secant of x times secant of x times secant of x times secant of x 4 times. The x is integrally part of the secant, if you want to think about it. Secant can't have, you can't just put this, like some of my, less careful calculus students from the past when they're using calculus stuff will sometimes even write stuff like this, and whenever I see it, I just mark the whole problem wrong. And why is that? Because it's impossible to have secant or cosine or tangent or anything without an angle inside of it. Does that make sense? You can call it x, you can call it theta, you can have 30 degrees, you can have 2 pi over 3, but there should always be something inside of it. This without an angle means nothing. Does that make sense? So I'm hoping that answered your question. Like the x is part of that. It's really just like x to the 4th power. And if you had x to the 4th power and you took x squared out of it, you'd have x squared left. Does that make sense? If you have secant squared and you take all of it out, divide it by itself and you get 1. Okay, good questions, guys. All right, so from there, I think we probably want to go and use that identity we just used a second ago. So secant squared we can change into what again? It says right there, tangent squared plus 1, right? You can change this secant squared into tangent squared plus 1 also if you want. I think I want to because looking down the road I see tangents. So I want to be trying to change these into tangents if I can, and I clearly can. Oh, gone. So this says tangent squared plus 1 times tangent squared. So look at your goal and tell me how we're going to get there, because there's one more step and the last step's pretty easy. Distribute, right? You distribute this to that. It's tangent to the 4th. Distribute this to that. It's plus tangent squared. Yes, that's what we were trying to get. Now, in identities, is there always one way to do it? If it's an identity, yeah. But there's usually multiple ways to do it. It's a question of flexibility. The value of this is not just learning some stuff about trig that's good. I mean, yes, that's true. You need this kind of stuff in calc and stuff like that. But it's also going to make you much more mentally flexible. If you want to do well in your ACT, take this assignment seriously because it will start to make you more flexible, more good at problem solving. It's all about the problem solving here. So they're really good kinds of problems to do. Let's look at 1 or 2 more. Let's see. What have I got? And you guys have the weekend to practice some more of these. I was going to do this one. Let's try this one. And some of the ones on this worksheet, they're a little bit tougher than the ones we did last time. They're using the same identities, but some of them are a little harder. Some of them are not. It just depends. I didn't put them in order of difficulty or anything like that. So let's try this guy, and then we'll just see if we have time for one. Which side do you guys want to start on? I think it's a toss-up again. Any preferences?
Right.
You want to go on the right? Because are you thinking about what you could do? That's a good idea.
Yeah.
If you go on the right, you could like expand it. Nice. Let's do that. Okay. And if we get stuck, we'll just start over with the other side and maybe see if we get anywhere with that. Supposedly, though, these are equal. So if their book is not lying to us, which, by the way, if you suspect I screwed up, because I did make up a lot of those in my head as I went. If you suspect I screwed up, because this is a new worksheet, how could you check to see if it's really an identity? Put the left side in Y1 in your calculator. Put the right side in Y2 in your calculator. And if they're truly equal when the graphs come out, whatever the graphs look like, they had better be copies of one another, shouldn't they? If they're truly equal. So that's a good way to test. They should all be good, though. Anyway, so you guys were thinking to expand this, right? So let's see. So we're going to write it down twice then. Okay, distributing. I get a cosecant squared right here. Here and here is minus cosecant cotangent. Here and here is another minus cosecant cotangent. Here and here is going to be minus cotangent squared theta. We good? Miss Muniz? Oh,
I'm just
okay.
trying to write this all down. So like
Yeah, I'll give you a second. Are we good? You guys awake?
Cosecant theta minus cosecant equals
You could use Pascal to do this. Yes, that's the way I do it. Gosh, but making sure everybody can do it. So there's a mistake. Where's my mistake?
number 1.
Jensen, you have an idea?
Get rid of the two cosecant cotangent.
If they were plus and minus, then you could, but they're like terms. We're going to put them together just for like terms. That's good. That was not my mistake, though. Where's my mistake? Okay, so I'm going to do, Jensen said we can put these together. I think there's 2 of them then. It's not looking like that yet. I don't know, this is a tougher one, I think. Let's see. This has fractions in it. I see 2 things we could probably do. We could either start to try to use reciprocals. I think I'm going to do that. This also has squareds in it. As soon as you see squareds, you should be thinking about versions of this. And there is a version of this which involves cosecant squared. Here it is. I don't remember it. I always mess it up if I don't redo it. So if I want cosecant squared, that's 1 over sine. Let's see what the identity is for that. Cosine over sine's cotangent. 1 over sine's cosecant. So we could use this if we want to, but still I'm not going to be getting these kind of fraction dudes over here. So now I think I'm going to just go with this way. I'm not sure. But see, these are the kinds of decisions you have to be making yourself, and the decision-making process is the thing that's going to be challenging. So, cosecant squared, besides using that thing, you could also write it as 1 over sine. Cosecant is also 1 over sine. And cotangent, how do you write that? Why don't you guys finish that step for me? Turn those all into fractions. There we go. At least I have some fractions now. That's maybe going to be helpful. Those are nice because they already have a common denominator. You see it? The denominator, all three terms, is what?
Sine squared.
Sine squared. That's cool. So we've got sine squared on all of these already. So let's see. What do we have left on top? We've got 1 minus 2 cosine plus cosine squared. This is a tough problem. I don't even know if I gave you guys any that are on this level, but I might have given you 1 or 2. It will require some experimentation. It will require some trying different things. Now look at that. Look at the top one up there. I'm sure you guys look at them and are like, no way. Totally different things, right? I don't. I look at them and say that's the same thing. Because I have more experience than you. But how are you going to see it? Because I don't know where to go next after this step. It's a little confusing. So, what can we always do at any point in this process?
Start over.
We could start over on this side, but I think we're doing some good work. We're making some progress. We could also always go to the other side and start working that down. Now, you can't work on both sides. This is not an equation, guys. You cannot work on both sides. But you can look and see where you get with one, look and see where you get with the other, and see if you can link them up at some point. That's what you do on the hardest problems. You shouldn't need that unless you've really tried it several times. Okay, does that make sense? Let's take that other side and see if we can do anything with it. We're looking for the aha moment. We want to be like Archimedes in the bathhouse when he suddenly figured out how to fill the king's crown.
Or we could be like
How to figure out the volume of the king's crown without melting it down and making him mad. We want that eureka moment.
No, it's
Okay, here's a strategy. You definitely want it in your notes. You might need it on 1 or 2 of those problems. It's one of the sneakiest strategies in identities. For all
I
time.
don't think so.
Use a clever one. We've seen clever ones lots of times in this class, right? Once or twice so far. We haven't done it for a while, but we've done a conjugate clever one. I'm going to do a conjugate clever one. You can multiply something by any form of 1, and it doesn't change what it is. That's 1, right? You can just totally cancel that out. How'd I pick it? Well, because when I see stuff that's like 1 plus and 1 minus, my mind just goes straight to a conjugate. That's experience. You guys will have that experience in under a year if you're working hard. As many of you are. Let's just see what happens. Let's expand it. Let's go on the top. 1 times 1? All right. 1 times negative cosine? Yeah. What else? Yep, got it, Dalton. And the last one? Which will be... Then on the bottom we get 1. We'll get a minus cosine and a plus cosine. That will go away, Jensen.
Okay, well, couldn't you just like slice the top one on the left and the bottom one on the right? Is there the same when you're multiplying? So can't you just cancel those out?
Can I cancel these out?
No, the other way around.
These?
But then
Yeah.
you get left with the same thing.
Then we'll get left with the same thing. You could, but it won't,
Oh, I
it won't
thought
take you further.
I was
Good
asking-
question.
I was just thinking.
Yeah. And if you're doing the same
Well,
problem-
What's on the top here?
Finding that. Yeah.
I'm smart.
Does that look familiar?
It's right there.
Now, last step, somebody's got to tell me. The bottom's obviously not the same, or is it?
It is.
It is. Why, Kosh? Because the fundamental trig identity, I erased it, it was up here in the corner a second ago, right? Is sine squared plus cosine squared is 1. So that means sine squared is also, if you subtract, 1 minus cosine squared. So this is sine squared. There's the link. We worked it from both sides. So to finish this problem, if you use this strategy, which you shouldn't need except maybe on 2 or 3 of yours, those will be the challenging ones. Put it up back together. So we started here, expanded it, combined some like terms, use the reciprocal identity, common denominator, then we got stuck. What's the next step? That's very hard to see if you're working from this side. It's to change sine squared into 1 minus cosine squared with the identity. And it's to write this factored. That factors as 1 minus cosine, 1 minus cosine. It's just a harder factoring problem, doesn't it? Because that's what we did up here. And then this is difference of squares factoring. 1 minus, 1 plus. Jensen, this is just set up for you.
Hey. Okay, so here's what we're gonna do. We're gonna do that thing where
Oh, no, not that again. I heard about that.
just gonna slice it just like that. Just like yeah.
I'm going to write this in red. We got to, because we earned this.
Do we earn the box?
We earned this box by it. You're right. Very nice. So, this is a problem. It will take you some time, some effort to get through a problem like this where you guys are developmentally right now. If you do it, I bet you will feel more proud of yourself than you've ever felt about mathematics or any other academic class if you solve a problem like this.
Mr. McGee.
Gotta earn it though.